Have you ever stopped to wonder how AI actually learns anything? I mean, we talk about it all the time, but what's really going on under the hood? How does a piece of code go from knowing absolutely nothing to doing things that seem, well, intelligent? Today, we're going to pull back the curtain and look at the engine that drives it all.
So, to make this real, let's just start with a simple, classic question. How on earth does a computer learn to look at a photo and know, hey, that's a cat? You know, it's not like someone programmed a bunch of rules like, if it has pointy ears and whiskers, it's a cat. Nope. The amazing part is that it learns from experience, kind of like we do, but the process is way, way different.
So the whole idea behind this is based on something called artificial neural networks. And yeah, the name says it all. They're directly inspired by the blueprint of our own brains.
See, when we learn something new, the connections between our neurons get stronger or weaker. It's a biological thing. An artificial neural network tries to copy that. It also learns from its mistakes, for sure. But here's the big catch. A machine needs a cold, hard number. It needs a precise mathematical way to measure exactly how wrong it was so it can figure out how to adjust its millions of tiny internal knobs.
And that brings us to the first crucial piece of the puzzle. Before the network can get better, it needs to know how badly it's doing. It needs a scorecard. That scorecard is called a cost function. You might also hear it called a loss function. Just think of it like this. It's a special formula that looks at the network's guess. You know, I'm 90% sure this is a dog, and then compares it to the real answer, which was cat. Then it spits out a single number. If the number is huge, the mistake was huge. If the number is tiny, it was pretty close.
And that's it. That's the entire game. For an AI, the whole goal of learning is just to get the lowest score possible on that cost function. That's its only mission. Make that number as close to zero as it can.
Okay, so the network knows its score. Now what? How does it actually lower the score? It needs a strategy, right? A way to find the settings that will give it the smallest possible error. And this is where a really beautiful and clever algorithm called gradient descent comes into play.
The best way to get this is to use an analogy. Imagine that cost function as a massive, sprawling landscape. It's got huge mountains and deep valleys, but it's totally covered in thick fog. The high points, the mountaintops, are where the error is big. The lowest points, the bottoms of the valleys, are where the error is small. And our neural network? It's like a hiker that's been dropped somewhere in this fog, and its only job is to get to the lowest point possible.
That's exactly what gradient descent is all about. The name sounds kind of complex, but it's really intuitive. The gradient is just a fancy word for the slope of the hill, right where you're standing. It points in the direction of the steepest uphill climb. So if you want to go down, you just take a step in the exact opposite direction. You descend.
So our hiker strategy is actually super simple. It starts at some random spot. It feels the ground right under its feet to figure out which way is the steepest way down. Then it takes a small step in that direction. And from that new spot, it just does it all over again. Check the slope, take a step downhill. Over and over and over. Each step gets it a little bit closer to the bottom of a valley, a place with a very low error.
But wait a second. This brings up a huge question. It's easy for a hiker to know which way to step, but our neural network isn't one thing. It's made of millions of tiny adjustable parts, these weights and biases. How in the world does it coordinate all of them to move together in the right direction? Who tells each individual little part exactly what to do?
Well, the answer to that massive coordination problem is the second piece of our engine. And honestly, this is the real magic behind modern AI. It's called backpropagation.
You can think of learning in a neural network as a two-step dance. First, there's the forward pass. That's when you show it an image. The information flows forward through the network, and it spits out a guess. But then comes the most important part, the backward pass. This is where the learning actually happens. The information about the error flows backward, from the final guess all the way back through every layer of the network.
And that's backpropagation. The name tells you exactly what it does. It's the backwards propagation of errors. It's an incredibly clever way of figuring out how much blame each and every one of those millions of connections deserves for the final mistake. It tells each part precisely how to change to make things better next time.
Now, just pause for a second and think about how mind-bogglingly hard that problem is. How do you efficiently assign blame across millions of interconnected parts? I mean, changing just one of them could affect everything else down the line. It sounds like a computational nightmare. And this is why backpropagation was such a revolution. Get this. The simple brute force way to do this for a network with 1 million connections would require you to run through the network over 1 million times just to make one tiny update. But backpropagation? It does the exact same calculation, gets the exact same answer with just one forward pass and one backward pass. It's not just a little faster, it's astronomically more efficient. It's what makes training these huge models even possible.
As the researcher Michael Nielsen says, this isn't just some neat trick. Today, backpropagation is literally the workhorse of all machine learning. Its rediscovery and popularization in the 80s is what truly unlocked the AI revolution that we're living through right now.
So let's put these two big ideas, gradient descent and backpropagation, together and see the whole engine in action.
Here it is, the training loop. Step 1, the network makes a guess. Step 2, the cost function gives it a score on its error. Step 3, gradient descent finds the best downhill direction to lower that score. Step 4, backpropagation calculates the exact corrections for every single connection and applies them. And then you just repeat that loop, again and again, millions or even billions of times.
And really, that's the secret sauce. This simple, elegant loop of guess, measure, correct, repeat, that is the fundamental engine powering the most sophisticated AI that you interact with every single day.
Seriously, every time Netflix recommends a show you might like, or your phone automatically tags your friends in photos, or a chatbot actually understands what you're asking, even when a self-driving car makes a decision, it's all powered by this core loop of gradient descent and backpropagation, tirelessly working to make that error number just a little bit smaller.
So, the next time you see an AI do something amazing, you'll know what's happening under the hood. It's not magic. It's just a hiker in a foggy landscape, taking one smart, efficient step at a time, over and over again. Which leaves us with a pretty deep final thought. If this powerful, yet fundamentally simple loop is how machines learn, what's the true limit here? What can't be learned one tiny calculated step at a time?